All right, let's get started. Hope you guys had a good weekend. So we are working on computing the gradient of this cross-entropy loss, which is what we need to do for logistic regression. And what's challenging about this loss function is, as you can see, it's kind of complicated. So our approach is to break this up into two parts. The first is to realize that there's a linear relationship between our parameters W, the things we want to adjust. And hey, could you guys stop talking? Could you guys stop talking? Thanks. There's a difference, or there's a transformation from our parameters to our scores Zi, and then the rest of this is a function of the scores Zi. So that's one way we can think about this. We can break it into those two parts. And so here we're denoting that first part, Z, as a function of W. As we know, we do this using some matrix A, which has a first column of ones, and then the rest of the columns are the features. And then this function here, if we think about it as a function of Zi, we can think about each of these terms. We can call that J sub I as a function of Ji. A function of Zi. And then that J sub I is relatively tractable. It's something we can work with. So overall, we have two stages. First, W goes to Z, and then second, Z goes to our cost J. And so we said the way we're going to approach this in terms of computing the gradient is we're going to use the multivariable chain rule, which looks like this. And this is something we're going to start seeing a lot of in this class. So here we have, this is basically saying the derivative of the cost with respect to the jth parameter is a sum over all the different training samples of the derivative of J with respect to Z, the derivative of Z with respect to J. So this is what we're going to use, and we just have to figure out these two components here. So the first one we can get from this relationship. So from here you can see dzi dwj, it's just aij. And then this other part here, we can get that from this function. And last time we derived this expression for that. So we have the ingredients, and so now we can put things together in terms of the gradient. So that's what we're going to do next. There's just a few details to take care of to make sure that this is done efficiently. Are there any questions about anything we have so far? Is it making sense? Okay. So it turns out that when we're doing this usually to do something like gradient descent. So for gradient descent, we need our gradient vector. But we also often want to monitor the cost to see how quickly it's decreasing. And so we usually want to compute both the cost and the gradient together. And so here's a piece of code that's doing that. We can take a look at that in a moment. And overall, the way we break this computation up is we do what's called the forward pass, where we compute So with the forward pass, we're basically given, at the input to this, we have some parameters W. So given those parameters W, you can compute these scores Z. From those scores Z, we can compute the cost. Show how to do that in a moment. And then in the backward pass, that's when we do the gradient. And for the gradient, we will also need to know the values of Z. And we've actually, this is exactly what we did on the previous slide, multivariate chain rule. And this is the expression we derived over here on the previous page. And this last piece here, we can think of this as, if we have a gradient vector, take the gradient of J with respect to Z, these would be the components of it. So that's kind of at a high level. We have this forward pass, and we have the backward pass. We're going to be doing this first and then the second. But in doing this, we want to be as efficient as possible. So we don't want to have redundant computations or computations that are wasteful numerically. So if you look closely, In the backward pass, we're going to have to compute this quantity here. But that quantity, that's going to be a little bit expensive to compute because of this exponential. So generally speaking, numerically, when you have to do an exponential like this, you end up having to use like a lookup table. That's maybe an order of magnitude more expensive than a multiply. So these are the sort of things you want to avoid, doing a lot of unnecessary things like that. And then when you look over here, this is what we had derived on the previous page. You can see that there's also this EZI thing. And so, the question is, can we make these look the same so that we can compute one of these terms once and then use it again? So essentially, we're going to do that. We're going to compute this, and we're just going to change this expression a little bit so that it's a function of this. So let's see how we can do that. So if we sneak in, okay, so first of all, if I put a negative sign in front of the log, that corresponds to inverting its argument. So that's where we get this. And then we can sneak this in to the numerator. And to counteract putting that in, notice that together this is going to be like the log and the e will cancel. This is like minus zi. So to counteract sticking in minus zi, we stick in plus zi here. And then as the last step, we notice that this fraction multiplied top and bottom by e to the minus zi is exactly this fraction. So that means we have things where we can compute this quantity once, and we can use it here and here later. And so that's going to make our code more efficient. Okay, any questions on that? So we're just doing that for efficiency reasons. And then one other thing is that we would like to avoid for loops in our code wherever possible. So this thing here, we could implement this using a for loop over I, but we'd like to do this using a matrix vector multiply instead, because that's going to be a lot faster. So let's try to take a look at how we can do that. So this is going to be the jth component of our gradient of j with respect to wj. So here's our gradient of j with respect to wj. Here's all the different components j. J would be like going down the rows here. And then we're sticking in these different components. So the first one, j is going to be 0, then j will be 1, and so on all the way to the end, where j is d. And now we have an expression for this scalar. This is our general expression. If we plug in the j equals 0, we get this. We plug in j equals d, we get this. All the other different values of j are in between. And now you can see that you can think of each one of these as an inner product between some a terms and the elements of this gradient vector. So here's, for example, in the first row, we have those a terms, and here's the gradient vector. So that inner product gives us this scalar. And then we can do something similar for all the other rows, like the final row would be this inner product, this gives us this scalar. And so when you look at it this way, we've actually built a matrix here out of our a coefficients. And if you look closely, the training samples are actually evolving along the columns, and the features are evolving along the rows. That's kind of the opposite of how the A matrix is usually constructed. So this is really going to be the A matrix transposed. And then over here we have nothing but the gradient vector of J with respect to Z. So at the end of the day, we have a nice way of computing this using a matrix vector multiply, no need for loops. Okay. Any questions on what we're done down here? Okay, so let's take a look at our code then. So this piece of code takes in the current W parameter vector. It takes in our training data X and Y. So the first thing it does is it computes this A matrix. It does that by making a column of 1s, sticking that to the left of X to get A. And we remember that's because of this. So once we have that A matrix, we can compute our Z vector using a matrix vector multiply. Then we compute vector of these terms. We do this with NumPy broadcasting, so we can do that like this. And then finally, we can compute this just by summing. Is that right? Yeah. This is just implementing this, again, using NumPy broadcasting. So you can see the code is very concise. A bit of effort is required for this matrix vector multiply. Only a little bit of effort is required for these nonlinear terms here. That gives us the forward pass. Any questions so far? Okay, then the backward pass, we just have to compute this, but since we already computed py, this part, that's easy. And then we compute the gradient according to this equation here, and that's it. And so now we have our cost, j, and our gradient, and we return both of those. Okay, so that's sort of the spirit of like how you attack a lot of these machine learning sort of optimization problems, where you break things into two stages, tackle them using the chain rule, and then implement them with this forward pass followed by the backward pass. We'll get into a lot more of this when we talk about neural networks. Okay, any questions on anything we have here? Okay, so your lab 6 will be very much in the spirit of this stuff. It's probably lab 6 is not even assigned yet. It will be assigned Saturday. But that's probably going to be the most challenging lab of the semester. So just, it gets into exactly this kind of stuff, but you're going to have a different cost. So you're going to have to derive things like this, implement things like this. It has very similar form, but you'll have to think through these details again at that point. All right. Any questions? Okay, great. So there is something a little bit inefficient about this. Let me see if I can. Let's see, is Vidal Sita here? No. What about Zachary Plotkin? No. What about John Zumberger? Yeah. So do you see anything about this that is sort of some extra work? Remember that we're going to be doing this once every iteration of gradient descent. Is there something we could do smarter?
Would it be something in the summation?
Well, I think so this part here, if you think, we're going to be recreating this 8 matrix every single time we call this function. Maybe we can create that A matrix first, once at the beginning, and then never again and again and again. So that's what we're going to do next. And to do that, we're just going to use a slightly different piece of code, something that is object-oriented, and that means we're going to be defining what's called a class in Python. So what a class has is it's basically like a container that has a bunch of functions in it, but it also has places to store data. And you've been working with these classes, like every time you program scikit learns linear regression, that is a class, that's an object where you instantiate the object. When you instantiate it, it does a bunch of initialization. The initialization stuff is done in this first function here. It always has this syntax. This is the initialization function. So when you instantiate the class, it runs this piece of code. This piece of code shows what you provide when you instantiate it. So here it says, let's provide it with the training data, matrix X, vector Y. And what this initialization code is going to do, as you can see, it's creating that A matrix. So we're going to do this once when we initialize it, and then never again. The other thing it's doing is it's going to store that computation as an internal variable. So these variables that are like self.something, those are the internal variables. So basically we're saying store y as an internal variable, store a as an internal variable, but you don't need to store, let's say, n or x as internal variables. Those things are just used temporarily to get the things we're going to store. And then the other thing it has is it has a function that we can call later after initialization that contains the rest of the code from the previous page. Okay. And here's how we would do it. When you instantiate the class, this is when you would first run it, you do logistic fun, and then you give it the data, and now it has a copy of this where it has run this initialization code. And then when you actually want to compute the cost and gradient, you do that class dot jeval, which is this function. And for that, you only need to give it the current parameters w, which here are called w naught. And then it computes the cost and the gradient. Okay, so it's basically more or less the same code as this, except it's breaking it up into this is done once at initialization, and this is done, the rest is done every time you call this jeval function. Okay. All right, so that's what is known as object-oriented programming. Any questions? I think most of you guys have seen this before. Pretty much all languages have this, even MATLAB has this. So all modern languages have this. All right, so now, as I said, this is something you'll need to do, for your lab, maybe sometime later in your life for some project. And in doing it, there's just a lot of places to mess up. There's all these computations you have to do on paper to get these expressions, and then you have to program all this stuff in NumPy, and there's just a lot of places where you can make a mistake. And that's very natural, we all make mistakes. So what's key is to have tools that allow you to find your mistakes and debug them. That's critical. And so there's a nice way of doing this using this linear approximation that we set up last week. So this is something we know is approximately true, and it gets more and more true as the difference between W1 and W0 gets smaller and smaller. So this is something we can leverage for debugging. Essentially, if we bring this JW0 to the left side, we can rewrite the expression like this, and we can easily program this to make sure that our gradient derivations and implementation are correct. So what we do is we randomly generate, let's say we randomly generate W0. So for example, in this code, we just make it using zero mean Gaussian random variables. And then we randomly generate a W1 that is close to W0. So one way we could do that is we can take W0 and then we can add a small Gaussian perturbation. And the perturbation here is controlled by step, and you can see step is a really small number. So now we have both our W and W0, W1 that are close by. And so now we want to check to make sure that this is true of our code. In some sense, this is going to check both the cost implementation and the gradient implementation of our code and make sure that they are consistent with each other. So we just run our log fun, our evaluation of cost and gradient at W0, and then we evaluate it at W1. And with these quantities, we can essentially look at the gradient at W0, inner product with the difference between our vectors, and we'll call this DJ predicted, and we can compare that to make sure that it is close to this quantity here. So for that latter quantity, we're just computing that directly here as a difference between those costs, and we're printing out these two terms. And when we print them out, the value itself is not really important. What's important is that the two versions of this, the predicted and basically both sides of these are consistent here to looks like 5 decimal points, 5 digits of precision at least. And that is because our step was small enough. So if you make your step too large, they're not going to agree as exactly. You don't want to make your step absolutely tiny, because if it's absolutely tiny, you could get into some numerical arithmetic issues. So for floating point precision, this is a pretty good step size. It's pretty clear that those two quantities really do agree, and that's what's important. Okay, so this is just a nice thing you can do once you finish programming things to make sure things work. And if this test fails, it's not really worth continuing. You got to go back and figure out where the error is coming from. Is it coming from your derivation? Is it coming from your code? That's additional debugging you got to do, but it's not really worth implementing or testing gradient descent if this stuff is not working. Okay, great. Any questions on this? Okay, so we're ready to implement gradient descent. And so we have simple gradient descent function. You can see we're giving it basically a pointer to our function that computes cost and gradient. We're giving it an initial guess of our W vector. We're telling it what the learning rate is, and we're telling it how many iterations to run that iterative algorithm. And so these things are guesses, you could say at first. So we're just guessing this learning rate. We're guessing this number of iterations. And we're going to run it, and we can plot how the cost evaluates over our iterations, and we can see whether these are good choices or not. And then in this function, basically we just initialize the main iteration variable W naught at our initialization W init. And then we have a for loop where it's really just 2 steps. Evaluate the cost and gradient at our current W naught, and then do an update of the old W naught minus the learning rate times the gradient equals the new W naught. So just sort of overwriting that W naught here. And really we're just iterating those 2 steps over and over again. Now for debugging purposes and just understanding what's happening, we are going to basically make a record of the costs, the different costs J naught that we've seen, as well as the different vectors W naught that we've seen. Now these things are optional. You don't have to do this. But at least plotting the cost is very useful. Maybe plotting or saving the W naught vectors, maybe that's not as useful. We're not even going to use them in the slides here, but the cost is going to be quite useful to us. Just some details. What we're actually doing here is we're setting up a Python list, and we're appending to a Python list. That's not NumPy, so in order to actually convert this to NumPy, we have another little piece of code that goes through the list and converts everything to NumPy arrays. Anyway, we finally return the final parameters, the final cost, as well as that history of costs and parameters as well. So, okay, any questions? So let's run it and see what happens. So we're using completely random Gaussian zero mean initialization, and we're setting here the learning rate 1e minus 4, number of iterations 2000. These numbers, by the way, over here, these are just the defaults. If you give it no specific learning rate or initialization iterations, it will use these values. But here, we're telling it to use these instead. So we run the code, and then we're plotting the cost versus iterations here. And you can see the cost is decreasing, which is what we want to see. Notice we're plotting on a log scale. That's usually much more interesting than plotting on a linear scale. If you plotted this on a linear scale, what would happen? It would basically, it would look something like this. And it would be hard to tell how things are changing. But on a log scale, actually log scale, it's easier to see how things are decreasing with iterations. And overall, what we notice is that even though we're running this for 2,000 iterations, things are basically evolving pretty slowly. our loss has decreased by maybe an order of magnitude, but as you can see, it's still going. In order to really minimize the loss, we should be running more iterations, or we could also, see maybe what if we use a different learning rate, step size. If we use maybe a different learning rate, maybe that would have sped things up. Maybe then we wouldn't need that many iterations. So these are things we can try. Okay, any questions so far? Okay, so let's try some different step sizes. So the orange curve is the one from the previous page. That was 1e minus 4. What if we try a slower learning rate? Well, not surprisingly, now the convergence is even slower. So, after 2,000 iterations, it's actually even worse than the orange one. Okay, what about a faster learning rate? So notice these are changing by an order of magnitude. So 10 times faster learning rate is the green curve. So the green curve, yes, at the end, it does do better for us. It converges to a lower cost. But as you can see, along the way, some kind of strange things are happening. So you can see that if you just look at the first iterations 2 and 3, you can see that the loss is actually increasing. It's because the step size was quite large and it was overshooting the minimum and was actually going to higher step sizes and there's higher losses. And then maybe kind of luckily it actually decreased the loss, but then it actually increased it. So overall, like at this level of learning rate, you can see that the loss is kind of decreasing overall, but it is doing it in a very non-monotonic way. So that might worry you. Maybe that's not quite optimum. And if you go to an even higher learning rate, then things, in here we're only increasing it by a factor of 2, then you can see things are really starting to get crazy. And in fact, it's never able to settle down to the bottom of the local minimum because it just keeps jumping around and it never really gets down there. So that's what you get with a really large learning rate. So it then remains to be, determine what is the optimal learning rate and is there a better one than this one? And, what is actually the minimum of the cost and so on. So those are all the questions we might have. So here's the final losses that we're getting. And here are the corresponding test accuracies. And so you can see that for these different losses, there's not a huge difference in the accuracy, but there are some differences there. Okay, so overall, when the step size is too small, you get slow convergence. But if the step size is too large, we get instability. So we want to really find the correct step size. Okay, any questions? Okay, great. So what we're going to do next is we're going to design a new algorithm that aims to actually adapt and determine the step size on the fly. And there's many, many ways you can do this. We're going to be using one called the Armijo rule. It's a pretty famous one. But again, it's not the only one. But anyway, that's the one we're going to learn about. And it's sort of based on this equation that we had derived and used earlier when analyzing gradient descent. So if you look at this equation, this is the cost at iteration k plus 1 if using step size alpha k at iteration k. So basically that's what it is. So like we start at iteration k, we have parameters wk. This is our cost at the previous iteration. And then we somehow take a step to give us wk plus 1. But here we're assuming, we're kind of saying what would happen if that step was based on alpha k. So you can imagine here, as you make different choices of alpha k, you can maybe hypothesize what would be happening to that cost. If alpha k is too small, our intuition is that we wouldn't really decrease the cost much. If alpha k was overly large, we would probably be overshooting, and this term would overwhelm this term, and we would actually make negative progress. We'd actually get a higher final cost than starting cost. So we really want to figure out what is a good choice of alpha k. So let me show you maybe this picture, and we'll come back to the previous page. So here is a picture of the cost at the next iteration for different choices of alpha k. And so you can see here, this would be alpha k 0. So as alpha k starts to increase, the cost at the next iteration comes down. Eventually it reaches some sort of optimal point. Then if your step size is too large, then you can see you're kind of overshooting. At some point, you overshoot and you end up getting the same cost, but if you increase alpha k even more, then you get even a worse cost. So ideally, we would like to somehow find this step size. And you can imagine maybe at that iteration k, maybe you could like set up a grid of step sizes, and you could like evaluate the cost over that grid. Right? That is something you could do. But doing so is kind of expensive because every time you hypothesize a step size, you have to compute the cost and the gradient. And as we saw, that involves some effort. And if you came up with maybe a grid of 10 values, then you finally, after 10 times the work of a single step, you would finally have a good idea of what that step size is. So that's pretty inefficient. You've done sort of 10 times the work in trying things before you finally choose the step you're going to take. So the Armijo rule is trying to come up with a simpler, more efficient way of doing that, where instead of testing a grid of step sizes, it basically has some current guess, call it alpha k, and then what it does is it computes a tentative update, wk plus 1, and it checks to see if this relationship is satisfied. This relationship says the cost after you take that step should be less than or equal to the cost of the previous iteration minus c times this first term here. So this c parameter, I want to emphasize, that c parameter is something we have to choose, the design parameter. Typical value might be like c equals 0.5. And to understand what this criteria is doing, let's plot it. Okay, so first, actually, let's talk about this dashed line over here. So what is this dashed line? So this is the update rule from the previous page. So what happens when alpha k is super small? Okay, if alpha k is super small, that means that this term here is much, much smaller than this term, which means you can pretty much forget about this term. And what's happening is well approximated by these two terms here. And you can see that this second term, how much you decrease, is linear in alpha k. So it basically says that when you have very small alpha k, this red curve is very well approximated by this dashed line. This is the slope of that red curve at the origin. So for very small step sizes, your cost after one step is approximately this. Now it's actually going to be a little bit higher because this is a positive term. So you could think of this dashed line as a lower bound on this red curve. So what then happens if you stick in this number c? Well, it takes that dashed line, which has some slope, and it actually sort of multiplies that slope by c, where c is a number between 0 and 1. So if this is the original slope like this, c times that would be, if c is 1/2, would be half that slope. And the Armijo rule basically says, check to see if your new update, which is the point on the red curve, is less than or equal to that point on the blue curve. So for any step size in this region here, you can see the point on the red curve will be less than the point on the blue curve. And the Armijo rule says, great, I'm going to accept that. Things are good. And that's because you really have made progress. Like, you've started here, and now you've decreased your costs somewhere over here. It's preventing you from choosing these points, because if you try this step size, it would compare this point to this and it'd say, nope, that's not satisfying my criterion, so I'm not going to accept that step size. And if it doesn't accept it, it basically says, let's decrease the step size and try again. So that's, this is sort of the approach then, is if the Armijo rule passes, you accept that tentative step. If the Armijo rule fails, you don't accept it, you go back to your previous WK, you sort of pretend you never took that step, and you set your step size a little bit smaller for next time, or maybe a lot smaller. You set up some parameter, beta decrease, this might also be 0.5, and this might say, half my step size, try again with that. And you keep doing this. You keep taking a tentative step, checking to see whether this holds. If it doesn't, you keep decreasing your step size until finally this holds. And if this holds, that means you really know that you have made progress. So this algorithm is guaranteed to always make progress whenever it accepts a step. And if it doesn't accept a step, it's decreasing its step size so that it will make progress hopefully the next time. Okay, and there's just one more point to it, is that maybe your step size, alpha k, is really conservative. Maybe it's tiny and you actually should increase it. So in order to do that, anytime you do have a successful step, it will say, well, maybe I can be a little bit more aggressive the next time. And so this is another parameter we have to set. Maybe this one is like 1.1 or something. So it says, increase my step size a little bit. Let's see if I can get away with a higher step size the next iteration. And it will keep doing this. It will keep increasing your step size until eventually it will fail. But if these parameters are set up well, it will pass many times and it will only fail a few times. And in doing so, it will be pretty efficient. Most of the work computationally is going to be used rather than thrown away. So that's overall how this works. I realize there's sort of a lot going on here. But I think this picture explains the idea best. So what questions can I answer about this? Yeah.
So if the rule passes, we increase step size and some other value as well?
So yeah, so if the rule passes, so remember this is like a tentative. So we computed this tentative update. So if it passes, we're like, good, I'm going to keep that. So that's one of the things I'm going to do. And then the other thing I'm going to do is just so that I don't get stuck at some overly conservative step size. If it passes, I'm going to increase my previous step size a little bit. See if I can get away with more the next time. So those are the things that happen if it passes. This last one, you don't always see this in different descriptions of the Armijo rule, but this allows you to not worry so much about choosing a too low of an initial step size when you set this up. Because if you set it too low, it will eventually grow it until it will get to a good value. Right. What other questions do you guys have? Is it making sense overall? All right, so let's take a look at what happens when we run this. So the code is not too complicated. Here's where we take our gradient step. So this is W1 is our tentative update, and then we evaluate the cost and gradient at that tentative update, and those are J1, JGrad1. This is the line where we check to see if the Armijo criteria is satisfied. So here's C, here's our learning rate times the norm of the gradient squared. And if this passes, then we accept the update, meaning the W0, the main iterate, is set at the tentative one. The cost is set at the tentative one. The gradient is set at the tentative one. And the learning rate is increased a tiny bit. But if it fails, then we basically don't use any of these new parameters. All we do is decrease the learning rate, and we come back, try again, using the same value of W0. Okay, so let's look at what happens here. Plotting versus iteration, plotting the loss and the learning rate. And again, this is a log scale. So this is iteration 1, this is iteration 2, iteration 3. And you can see that the loss actually has not decreased for the first few iterations. This is because it failed the Armijo rule. The step size or learning rate we set initially was just too aggressive. And so you can see what it did is it decreased it. I think we set it at 1e minus 3. It decreased it by a factor of half. So now it's like 5e minus 4. Even that failed the rule. So then it decreased that by a half. And finally, it passed. So now it actually made progress. And it actually passed for many iterations. You can see all these iterations. It was successful in decreasing the loss. And simultaneously, the algorithm's like, well, maybe I can be a little bit more aggressive. So for this, I think I'll probably set it up to use 1.1 as the increase factor. So it's just gradually increasing it. And you can see it's actually getting away with a lot of these increases all the way until, an iteration, 25 or so. So from iteration 3 to iteration 25, it was successful. But then finally, at this point, it failed again. And it failed once, it was successful, failed again. But then it was successful for many other iterations and so on. So you can see the loss kind of, it's usually decreasing. Once in a while, it has these plateaus where it doesn't decrease because it's failing the Armijo rule, but in that time, it's sort of recalibrating the step size. And what's interesting when you look at the overall step size or learning rate over these iterations, you can see that there's sort of like a baseline learning rate where early in gradient descent, it's at a part of the cost surface where it has to be conservative at its learning rate. But later, as it gets closer and closer to the solution, the shape of the cost surface is actually changing, and it can get away with a much larger learning rate. So this learning rate, the sort of optimal learning rate is really changing with iteration, and the Armijo rule is figuring that out. Okay. And so the final value that you get after 2,000 iterations is smaller than any of those 3 or 4 examples we tried earlier, and the test accuracy is actually a little bit larger. So this really did work out for us in the end. Yes?
For the optimal learning rate, this is something overall that might happen to everything that increase based on the iteration of
This may or may not happen. It just happened for this cross entropy loss.
So it can have any shape based on the...
Yeah, we can't generalize, right? Yes.
But for this example, does that mean that the loss function was bumpier in the beginning and then it kind of smoothed out?
Yeah, basically. Exactly. Yeah, and that's something very common in machine learning where the kind of topology of the cost surface changes depending on where you start and where you end up. Yeah. And there's all sorts of, so this Armijo rule is really set up for convex type of problems, because what this is going to do is if you have a local minima, it is going to make sure that you end up there. It is not going to jump out of that local minima. But as we'll see, once we start talking about non-convex problems like with neural networks, you don't actually want to settle in the closest local minima. You actually want to jump out of there and land in a better one. And when you want to do that, you actually use very different style of algorithm. Armijo rule would not be the right thing to use for those non-convex problems. So this is really set up. It's going to minimize this convex problem. It's going to get you to the locus, the nearest local minima, which is where you want to be in a convex problem. But it's not what you want to use in all cases in machine learning. Okay. All right, so that's the Armijo rule. Any questions? Okay, it's making sense? Okay, all right, so we're getting close to the end of this unit. So, yeah, we just have really a few things left to talk about. Maybe we can even finish it today. So I've talked sort of loosely about convexity and said that convexity is this nice property where Essentially, convexity means that any local minimum is also going to be a global minimum. So it's enough to search for a local minimum. You know that then you found the global minimum also. So, okay, what is this convexity stuff? So to understand convexity, we first have to talk about convex sets, and then we can also talk about convex functions. So basically, a convex set is a set where if you take any 2 points in the set, we'll just call them x and y, and if you take a number between 0 and 1, and you essentially use that number t to sort of linearly interpolate between those 2 points, you have to make sure, if this set is convex, then you're guaranteed that no matter which 2 points you start out with, all the points in between them will also be in the set. So this is sort of an illustration of a convex set. Here's an illustration of a non-convex set where we can find 2 points that are in the set. When we look at all the so-called convex combinations of points between them, we actually get points that are now outside the set. So this is a non-convex set, whereas here you can see we have a convex set. No matter which 2 points I choose, all points in between would be in the set. Is that idea making sense for convex sets? Okay, so examples of convex sets would be circles, squares, ellipses, all numbers in Rn, so the field of n-dimensional tuples of numbers, or even hyperplanes in Rn, or half spaces in Rn. All those are convex sets. Okay, any questions on convex sets? Yes?
What's that half space?
Oh, half space, so if I take like the entire real domain and I cut it with a plane through the origin, and I say everything on that side of the plane, and nothing on the other. So now I've like chopped this into 2 spaces. Yeah. Okay, so those are convex sets. Now convex functions, a function is convex, first of all, if its domain is a convex set, so that's why we had to talk about that. But also, if you look at any, again, 2 points in this convex set, you need that convex combinations of the inputs applied to the function will be less than or equal to a convex combination of the outputs of the function. So this is best illustrated, I think, with a picture again. So this is just where we have, so the input here is just one-dimensional, so x and y would be scalars. And so this would be x here, this is y over here. And if you look at the function of convex combinations of x and y, that would give you this curve. So the points along the real axis in between, that'd be a convex combination of x and y. And then we evaluate that, put that in the function, and we get this, let's say this point here. Or if this is my convex combination of x and y, I evaluate that with the function and I get this, and so on. So this is the left side. We need that to be less than or equal to convex combinations of the functions evaluate those original points. So if I look at x, I evaluate fx there. I have here a y, evaluate fy there. And then I look at a convex combination of the function outputs. I need that is above this, or let's say not below this, this other function applied to the convex combination. So basically, this is the definition of convexity here. So you can see, that this function is definitely convex, but I think I probably have an illustration. So like this one, would fail that because I could come up with a convex combination of x and y, evaluate the function there, and that is actually less than, this is my convex combination, I evaluate the function there, that is less than, or greater than this here. So this would violate that definition of convexity. And as also you can see here, the presence of multiple local minima, whereas here you don't have that. Okay, so that's that's the definition of convexity. Any questions on that? Okay, so let's talk about some examples. So starting the simplest case, let's say I have a linear scalar function. This is a convex function. If I have x as a vector, and by the way, everything we're saying here, the output function has to be scalar. The input could have multiple parameters, but the output must be scalar. Okay, so if I have a vector input x, then this is how I'd build a linear or maybe affine linear function. This is also convex. Quadratics, this is scalar quadratics, are convex if the coefficient on x squared is non-negative. So that would give you functions like, parabolas like this, or if a is exactly 0, it would give you a line where you're back to this. But if a is negative, then you get a concave function, which is sort of the opposite. So that's why we have that. We can generalize this idea beyond quadratics just by looking at a function f and its second derivative. So you can see like the second derivative of this function would be 2a. And so essentially we need that second derivative, if it exists everywhere, it needs to be non-negative everywhere. So that's sort of you can see why that's maybe true based on this. And if you want to extend that to vectors x, instead of looking at the second derivative, you look at basically the matrix form of the second derivative, which is called the Hessian matrix. That matrix must be positive semi-definite, which is sort of like the extension of this to matrices. Okay, so this is how you could, some shortcuts to testing if a function is convex or not. These are sufficient conditions, not necessary. Other functions that are convex are any norm is going to be convex. Also, anytime you have two convex functions, f and g, their sum is convex. You can get convexity with composition as well, except that the outer one needs to be non-decreasing as well as convex. And if you look at, put these two terms together, so we know that RSS is convex. It's sort of based on these ideas. It can be shown that our binary cross-entropy or cross-entropy losses are also convex. And because we can add norms to them and have them be convex, so are all the L1 or L2 regularized versions that we've seen. So this is sort of like everything that we've looked at in this class so far in detail. So RSS, ridge, lasso, everything we looked at for logistic regression, all that stuff has been convex so far. We'll start to move into non-convex things when we talk about neural networks. But for now, pretty much everything's been convex. Okay, so so that's convexity. Any questions on convex functions? Okay, so and then I sort of said this already, but this is why we care. So if a function is convex, and if x is a local minimizer, then it's also a global minimizer. So you could have situations like the following with a convex function. You could have a function that has a big flat spot. So that, in this case, all of these points are equally good. There's many local minima. They're all global minima. This is a convex function. I guess what I'm saying is the minimum may not be unique, but all the local minima are also global minima. Another thing about this function is that it's not differentiable. So some of these things that I talked about earlier wouldn't really apply there. Convex functions could be non-differentiable, have these sharp edges. But the point is that if I somehow found this point or this point, I'd be equally happy because they have that same minimum loss. Okay, so that means I could run something like, if it was differentiable, I could run small step gradient descent, and if it converges to a local minimizer, then I know it's also converged to a global minimizer, and I'd be happy. Okay, so that's perfect time to stop for today. Any last questions? Great. Okay, see you guys on Wednesday. We'll quickly finish this up and start on the new unit.